So we are starting up with the unit number 8, chapter 8. What is the topic? Heat changes associated with the chemical reactions. Okay, heat changes related to the chemical reactions. Okay. So to start up the lesson, we need some small basic ideas from written, that is about the physical change and chemical change. Can you remember what they are? Physical changes, chemical changes. Physical changes means only the physical state, physical nature is changing. Example, you take a rock, okay, a larger crystal, you break it, it breaks into small pieces. Okay. Ice cube, you hammer it, you beat it, breaks into small pieces. Physically changing. Is there any new substance produced? No, nothing new produced. Same thing broken into pieces. Right? Let's say water, you boil it, becomes water vapors. Is there any other vapors produced? No water vapors. Collect the water vapors and condense that, you get water. Nothing else. Physical changes. No new substances, you can get them back to the original state. Chemical changes means new substances are produced. Maybe building up two or more components combined together, making one. Building up. Anabolism we see. Building up reactions. Or one component breaking into two or more components. Breaking down. Catabolism. Catabolism. Right? So anabolism, catabolism. So actually those words we are basically using within the biology structures. Okay. So anyhow, building up reactions, breaking down reactions. During these, new substances are produced. New substances are produced. So these new substances might be different in properties. And you can't take them back to the origin. Okay, you can't take them back to the origin, the original level. So these are chemical changes, and chemical changes are what we name as chemical reactions. Chemical reactions. These chemical reactions we are dividing in different ways based on different aspects. Here we are gonna take under the heat. Again. Now, if there is a chemical change happen, chemical reaction taken place, how do we observe if it is really a chemical change or a physical change? Physical change? Because of some observations, some evidences are there. What are they? We can see something like a glow, a flame, a light, a sound goes out. Or maybe a gas bubbles moving out. Liberation of gases, you can see. Some substances depositing down, you can see. A color change. A new color is given, or maybe between pale to dark, color is changing. Or color becomes colorless. Certain color becomes colorless. Okay. Or else a heat change is happening, temperature is increasing or decreasing. So something like this, if it is taken place, maybe one or two of these observations are given, it is a chemical change. You understand what a chemical change is? Right? Any of these observations are given. Any of these observations are given, maybe an odor change, the smell change, a different smell is given, different color is given. So any of these changes happen, this is a chemical change. Okay? Means a new substance is produced. Right? So here we're going to highlight the exchange of heat. That is what we need in our lesson. Means during a chemical reaction, sometimes temperature increase, sometimes temperature decrease. Depending on this, we divide our lesson, the chemical changes depending on the heat. Okay, the chemical reaction depending on the heat into two exothermic reactions and endothermic reactions. Exothermic reactions and endothermic reactions. So what is exothermic and endothermic? That is what we are going to learn. Okay, what is exothermic and endothermic? So let's write this first and then we will discuss. The chemical reactions. The chemical reactions. The same two boxes are given. Okay, the chemical reactions happening with the evolution of heat. Happening with the evolution of heat. Are called exothermic reactions. Are called exothermic reactions. are called exothermic reactions. Okay, and write there down. Reactants become the products plus heat. Reactants become the products plus heat. We'll discuss about, okay. Reactants become the products plus heat. Endothermic reactions also you wrote, right? The reactions taking place with the absorption of heat. Right? The reactions taking place with the absorption of heat. Right. Wrote the reaction also, right? Okay. Now, what is this actually? The heat reactions. We divide these heat reactions into two. Exothermic reactions and endothermic reactions. Endothermic reactions. Exothermic means, let's say when a reaction happens, okay, during the reaction, heat is lost to the system. Heat is lost out to the system. And you measure using the thermometer. That means in a beaker, you're going to apply A plus B. Okay. Within the beaker, you have the thermometer. Okay. Now, once you apply A and B, measuring the initial temperature, after a while, you can see the thermometer reading increases. Thermometer reading increases. What's the reason here? The reason is when the A plus B reaction is happening. Okay, actually A plus B means actually A and B, two components, and they are reacting, but they produce what they break up or whatever. Okay. Now, or maybe a breakdown, right? So basically this happens to the breakdown of the components. Now during the reaction, heat is lost out. What is happening during the reaction? Heat is lost out. heat is lost out within the beaker. So beaker's temperature goes up. The mixture, the solution's temperature goes up. So if the heat is lost out in a reaction, if the heat is lost out in a reaction, these reactions are called exothermic reactions. What reactions are they? Exothermic reactions. So what's happening here? Heat is released. Heat is released. Because of the heat is released, temperature increases. So here the temperature increases. Okay. I'm releasing out the heat, so the surrounding temperature increases. Because I'm releasing out the heat. So the heat is added there, temperature increases. Endothermic means when a reaction is happening, it is absorbing the heat. What it does? It absorbs the heat. And the reaction, what I do? From my surrounding, I'm absorbing the heat. When I absorb the heat from my surrounding, the surrounding temperature, what happens? Goes down, right? Because it is losing the heat, no? Surrounding temperature goes down. So, surrounding temperature goes down. This happens because of the heat is absorbed. So, when the heat is absorbed, temperature goes down. And the heat is absorbed, temperature goes down. Okay? Did you understand that? In exothermic, you are losing out the heat, so the outer temperature increase. Your temperature decrease. Outer temperature increase. When you absorb the heat, outer temperature decrease. Now, usually when a reaction is happening, reactants are what converted into products. So what's happening here? Heat is released. So the reactants become the products releasing heat. Reactant become the products releasing heat. Product plus heat. And what happens here is absorbing heat, right? So reactants plus heat becomes the product. Reactant plus heat, absorbing the heat. You understand the difference? This is releasing heat. So it's something like reactant minus heat. Releasing means minus, no? Minus heat. When you take the minus, you say plus heat. Simple. Reactant plus heat, you are absorbing the heat. Okay. You were 1000. Imagine 1000 units of heat are there. You are releasing out 200 means how much you have now? 800, right? Correct. You had 1000. You are absorbing 200 means how much is there now total? 1200. So you see now, accordingly, when I take the heat of the reactant and the heat of the product here, reactant, product. Heat of the reactant, heat of the product, I take whose heat is more heat. I was 1000, releasing 200, and I become the product of 800. Reactant 1000, product 800. Because you are releasing out heat. You understand? You had 1000, you are releasing 200, you become 800 product. Who is more? Reactant or product? Reactant more. Reactant more. Because of that, you are releasing and becoming the product, isn't it? You understand? You are releasing out means you should be more, right? And you are becoming the product. So, reactants more here. That is the third point. What is the third point? Reactants more. Okay. What happens is you are 1000. You are adding 200. You become the product of 1200. Who is more? Product is more. Product is more. So products more. So the third point, product is more. Okay. Reactants more, products more. More. What is more here? The heat is more. Okay. Products heat is more. Right. Now I'm going to take the delta H. Delta H means the heat change. Heat change. Usually the heat change we are taking from final minus initial. Now, usually whenever we are up to find out a difference, 2 minus 1 will take velocity, final velocity minus initial. Right? So, momentum came, final momentum minus initial momentum. Final minus initial, 2 minus 1. Last minus first. So, who is the last one? Products. First one is reactant. So, how do I take product minus reactant? Correct? second minus first. Product minus reactant. I don't know the values, but I know when you take the difference, the greater value, okay, the once you take the difference, who has the greater value, that sign you have to give, correct? 5 minus 8. What is the answer? 3 minus 3. Greater value is 8. So I definitely know that reactant is Mohideen and reactant holds minus. So the value must be negative. Correct? Correct. HP, product minus reactant, should be the difference. I don't know the real numbers here, but I know reactant should be more. In an exothermic reaction, reactant should be more. If reactants are more and holding the minus value here, my answer should definitely be minus. Why? 5 minus 10 is minus 5. 10 minus 15 is minus 5. 15 minus 23 minus 8. Why? Always reactants more. Reactant is holding up minus 1. So this is my fourth point. And what about this? Delta H equal products minus reactant. Product is more. Means my answer should be a positive value. My answer must be a positive value. Clear the point? Okay. So negative value, positive value. You understand? Okay. Negative value, positive value. So exothermic reactions means heat is released, so the temperature is increased. Reactants more in heat, it is negative. What is negative? Heat change. Delta H is negative. These are the 4 points. One of the 4 points you ought to remember. Heat is released, temperature increases, reactants move, negative value. Heat is increased, temperature increases, reactants move, negative value. What about this? Heat is absorbed, so the temperature decreases, so products move, positive value. Positive value. These are the 4 components you have to compare always. Okay. So if any heat changes are given minus answer, minus means it should be exothermal. Any heat changes given as positive answer, plus mean should be another. That is something. And these measures are given in kilojoules per mole. Because for one component you can't measure it, it's very small. Can't measure means very small value, you can't take it to the questions. So for 1 mole of component only these measures are taken. Basically it is taken in joules per mole or kilojoules. Kilojoules per mole is what we are using in the energy level diagrams. So we have to draw energy level diagram for this, not the chemistry energy level diagrams. So to represent the energies, we have to draw the diagrams. Okay. So we take the diagrams in this way. Let me take the exothermic here in the thermic. Okay. When you come for the diagram, it's very easy. Just one vertical line and 2 horizontal lines. And here we mark energy in kJ mol minus kilojoules per mole. Okay, so both the sides same. Energy is measured in kilojoules per mole. Okay. Now, vertically when you go on a graph, value increases, right? Vertically, value increases. So when you go up, value must be increasing, and only 2 of them we have to mark. One is the reactant, the other one is the product. You have to mark only 2. Now for exothermic, who is more in? Reactant more in? Products less, right? So who I should mark in? Reactant or product? Reactant. I have to mark the reactants. Why? Reactants are more, and the products I have to mark here. And the reaction is always happening from reactant to product. So the arrow it should be down. Okay. Why the reaction is happening always from reactant to product? Input, processing, out. Input, reactant, output, boom, product. Processing is the reaction. Okay. So reactant to product, the arrow should be shown. Reactants more, products less. And what is happening here? Heat is released. So we have to show, look at the arrow head, moving out. So we write here, heat is lost. Released. Okay, released. Endothermic what happens? O is more, products more. Reactants less. Products more means I have to write the product here. This is a general graph and the reactants here. Now the reaction should be always from reactant to product, right? Output to input, it won't happen to input to output. So reactant to product you have to show the arrowhead. It should be a straight line. Okay. And now what's happening? Heat is absorbed, right? Heat is absorbed. Endothermic, you have to write here. Heat is absorbed. Heat is absorbed. Right? Heat is absorbed. So this is the general idea. General idea. Usually exothermic reactions are breaking down reactions. Let me say it was AB broken into A plus B. AB broken down into A plus B. And I'm giving you delta H is negative X. Delta H is negative X minus X. Now, minus means we know it is exothermic. How do we do that? Energy. Two of them are there. One vertical line, two horizontal lines. Okay. If it is minus, definitely exothermic. Reactants, products, and I know reactants move. Reactants move. Exothermic reactants move. How do I know it's exothermic? Because it's a negative value. Giving negative value here, it should be exothermic. So reactants move. Reactant is AB, right? Reactant to product. So reactants move AB, products less A plus B. And the arrow should be from reactant to product. Correct? Reactant to product. Arrowhead is from AB to A plus B. And the heat is lost, right? And I don't know if heat is lost now. Why? It is given. Delta H is equal to minus X. Minus X. The value is given. Kilojoules per mole. What is the unit given? Hot rate. So this is for exothermic reaction example. I have given ABCD like what is the equation for that equation is hot rate. Okay. What is given for reactants you are right here. What is given for products you are right here. With the physical state you are right. Okay. And what if it is A plus B becomes AB and I am giving you delta H is plus Y. Delta H is plus Y. Now plus means definitely you know positive value means endothermic. In endothermic who is more? Products move. Who is the product? Always from reactant to product. Who is product? AB. Who is the reactant? A plus B. And this is the graphs are both same, right? AB and A plus B. No, arrowhead changes. This goes AB to A plus B. This goes AB to A plus B, but it goes A plus B to AB. And what is happening? Heat is absorbing. Heat is absorbing. How much is the heat absorbed? Delta is equal plus Y. Kilojoules per mole. Or joules per mole. What is given? Did you understand? Okay. So this shows you heat is absorbed and this shows you heat is released. Minus X plus Y. Clear the point? So here also, what is the real equation given? From that equation, you have to pick up the reactants and products when you are writing. Clear the point? Is it hard? It's very easy. It's very easy. Okay. So exothermic goes with this. Endothermic goes with this. Okay. So this is all about exothermic and endothermic in simple. We are dividing lesson into two. First one, basic concepts. Basic concepts goes about 70%. 70 to 80% basic concept we can take. The second part is the heat change, one small activity. 20% like a small activity part is there. Just a calculation. Okay. So out of 70 to 80%, almost 50 to 60% we are done. This is a part. This is a concept. It is given in number of passages and all descriptions and all. This is the concept. And what I have to add with the remaining 30%? Some examples. Two activities each we discuss. Okay. Two activities are there we have to discuss. And some applications where we use this exothermic and where we use this endothermic. That's all. Then we will be coming up with some two diagrams we have to draw. So with that 30% is done. Remaining 20% goes up with heat change. Heat change, a small calculation part is there. Okay. Okay. I have given all the notes. Notes are there one by one. It is given. Summarizing this. So this is the part you have to remember. Did you understand? So tell me what is exothermic? Heat is released. Endothermic, absorb. What are the 4 points? Heats released, temperature increases, reactants move, negative value. Repeat it. Heats increase, temperature increases, reactants move, negative value. What about the endothermic? Heat is absorbed, temperature decreases, products move, positive value. Repeat it. Heat is absorbed, temperature decreases, products move, positive value. So these are the alternating, okay, parallel ones you have to remember. You understand? Clear? So take one complete page on your CR book. Okay. Divide it into left and right side. Okay. Write it in the same way. Now once you are done with this guys here, do highlight the parts. Use the colors. Two different colors you use. Once you are done with these, below you have to take these two diagrams. Can you see? These two diagrams. Use the rulers when you draw, use the pencils when you draw. And enter the make this particular part. Don't mix them. Somewhat, if you don't have enough space, go to the next page, take the same order. Take the topic as exothermic and endothermic. Okay. Please draw it. So this is all about this exothermic and endothermic reaction, the basic concept. So we have to head up with the tube now. Okay. We will read along with that. Exothermic reactions. Let's read. Hurry up. Now it says, why is that the temperature increase? Why temperature increase during exothermic reaction? What is the reason? Read. The temperature increases because of the loss of heat. Am I right? The temperature increases because of the loss of heat during the chemical reaction. During the chemical reaction. Exothermic. First page, okay, behind the first page. The temperature increases because of the heat loss. Right? Now the reason for this is energy in reactant is more than the energy in products. Energy in reactant is more than the energy in products. So underline that energy contained in the product is less than the energy contained in reactants. Energy, reactant moving, product is less. Underline it. So these two statements starting from here, you have to underline. Okay. So the illustration is given here. You can see this is what we just discussed and how it happens with the negative value. We discussed about that, right? So look at the activities then. What are the activities here? I'm going to take a container. Quickly read that, please. Quickly read that. I'm taking a container and half of the container filled with water. Okay, filled with water. Look here. And I measure the initial temperature. Okay, I measure the initial temperature. I'll mark it as I. Using the thermometer, I measure the initial temperature. Theta, it's not Q. Okay, theta. Theta is a correct word, but we say theta. Theta, no, you are saying, right? Theta is a correct term, right? So theta I, initial temperature I measure. Then what I do, I'm going to add sodium hydroxide. Whom I am adding? Sodium hydroxide. NaOH, sodium hydroxide, I'm going to add. Adding sodium hydroxide, I have to stir it with. I'm having a stirrer, a mixture. I'm mixing it. I'm stirring it. Or using a glass rod, I'm stirring it. And I observe the change in temperature. I can see the thermometer reading goes up. What is going up? The thermometer reading goes up. And I have to measure the maximum. How do I measure the maximum? I keep observing where it stops. After a while, it comes to a maximum amount and no more change afterwards. That means that is a maximum. Okay. So what I do, I record the final temperature also. Now when I consider these two, I could see this final temperature is greater than the initial temperature. Final temperature is greater than the initial temperature. So final temperature greater than initial temperature means what is the meaning? Temperature has risen. Temperature has been increased. If there is an increase in temperature during a reaction, what type of reaction it is? Exothermic reaction. So this shows you that it is an exothermic reaction. So adding sodium hydroxide for water is an exothermic reaction. Exothermic reaction. So same like another activity is there. What we do here? Here we're gonna take again another beaker. Whom we have now? We have dilute hydrochloric acid. Dil we write. Dil means dilute. Diluted means more water contained. Adding more water for few amount of acid here, right? So dilute hydrochloric acid we measure it and we measure the startup temperature. Initial temperature I measure. Okay. And then what I do, I'm going to add magnesium ribbon. 2 centimeters, 3 centimeters, whatever. We need only the concept. Because the values may be different. You don't want to memorize the same thing. Activities when it comes, don't try to memorize the same thing with the values. The statements you have put. Values don't, because it may change. Okay. So, at home, magnesium stripe. A small ribbon of magnesium. Small stripe of magnesium you have. Once you have that, you can see there will be a reaction magnesium with HCl reacting. Magnesium chloride will be produced, leaving out hydrogen gas. So you can observe hydrogen gas. You don't know hydrogen it is. But in a bubbling of gases, you can see evolution of gases. You can see. Okay. So now, again, what do? You take the maximum temperature rising up and you mark the temperature. And when you compare, final temperature is more than the initial temperature. You can see final temperature. So rising means anyhow final temperature should be more, right? So final temperature more than initial temperature. So temperature has risen up. Temperature rising up means what type of reaction it is? Exothermic. So two activities showing you here. Any reaction you consider if the final temperature has risen up, increased, means it is an exothermic reaction. Evolving out heat, releasing out heat, temperature change is increased. So it is exothermic. You understand? So both the reaction adding sodium hydroxide to water, adding magnesium ribbon for an acid, HCl, H2SO or whatever an acid, both of them are exothermic. Both of them are heat evolving out exothermic reactions. Clear the point? Okay. So we want this to be drawn. Look at your tube. Look at your tube. You have a small space opposite to both the activities. Okay. Can you see here? I don't want to draw it a bit larger. Small scale. One here, the other one here. Don't use this text box, okay? Don't use this text box. You have to draw front of the activity here and the second activity. Got it? Mark down like use the pencil. Formula. See. See. Imagine you do. So both of them at once. That would be coming up. No, not stir. Stir. Not enough that. This is a stirrer. It is a stirrer. Stir. It's a stir. You have to stir it when using a stirrer. Or stirrer using. If it is hard, stirring. Not this stirring. Okay. You mixing using a stirrer. Huh? Spoon. We don't use spoon here because it's a metal. And we have acids. We can't use. Yeah, it's a glass. Okay, take it as a glass rod. Easy. But you should know the word. Okay, it comes with the questions. Stir. S-T-I-R. Yeah. Previous one. Stir with glass rod. You have to stir it with glass rod or as a stir. Are you done? Yes. Now below that there's an activity, right? There's another example taken for this, actually the magnesium. This is the reaction. Magnesium plus HCl. What does it give? Magnesium with chlorine, MgCl2. And hydrogen gas goes out. Hydrogen gas goes out. So this is the reaction. This is a reaction. H2Cl2, 2. Balanced. So this reaction you have to write below. You have to write that reaction below. And then there is an energy box given there. Okay, there's a text box given, right? Within that energy level diagram for this reaction you have to write. Okay, you have to do. Shall I take this out? Done with this, right? So I want you to do this. Okay, first write the formula, the equation there now, and draw the energy level diagram. Don't use the word reactant and product. Use the reactants and products equation. Okay, fill it up. Inside the text box, you have to draw. Closer to the text box, you have a space right below the statement. There you write the equation. You understand? Okay. Please go ahead. Magnesium with HCl. Reactant magnesium chloride. Then he might have observed something. Now something should have happened. So no, I can't go to three. What? Now we have now I right. How do we do? Exothermic reactions, reactants are more. Who are the reactants here? Magnesium with the state you have to write, okay? And you have to balance, and the balance equation is what you are supposed to write here, right? And then you take magnesium chloride, it may be solid, say this is what AQ here, and H2. Now reactant to product, you have to show the element, right? Since nothing is given, you have to just write it as heat is released. Right? Heat is released. Write the physical states. Don't miss the physical states. And can you write it down here? No. They have to write above the line. Above the line. Okay. So fill it up. Endothermic also we discussed. Okay. Endothermic also we discussed. You can see here. What is endothermic? Look. Absorbing heat. So why is the temperature decrease? Underline, the temperature decreases because of the absorption of heat. Temperature decreases because of the absorption of heat during a chemical reaction. And the reason for that is the energy contained in the product is greater than the energy in the reactants. Underline that. Start from energy contained in the product is greater than the energy in reactants. Underline that too. And the energy level diagrams are given there. Example. You take water, measure the temperature, and sodium, ammonium chloride, solid ammonium chloride you add. For water, you add ammonium chloride. Mix it, measure the temperature again. You can see temperature will be decreasing. If the temperature is decreasing, what type of reaction it is? Endothermic reaction. Same way. Now we don't want to draw, you have the idea. Okay. So what is the reaction here? Adding ammonium chloride to water. Adding ammonium chloride to water. So this is an endothermic reaction. Endothermic reaction. Okay. And then we will write there in front of this. In front of the activity, right there. Adding solid ammonium chloride to water. Adding solid ammonium chloride to water. So it's front of the endothermic reactions. Right. Front of the activity. Adding solid ammonium chloride. Adding solid ammonium chloride to water. Solid ammonium chloride to water. Solid ammonium chloride. Ammonium chloride, you have to remember it is NH4Cl, okay? Ammonium chloride to water. NH4Cl. Ammonium chloride, NH4Cl. Ammonium chloride. Right. Second activity, write the opposite, the topic you write. Adding sodium bicarbonate to citric acid. No, just write sodium bicarbonate solution. Adding sodium bicarbonate solution to citric acid. Adding sodium bicarbonate solution, okay? Solution, not solid, solution to citric acid solution. Okay? Na2CO3. Okay? Fine. Anyhow, you see, once you have to measure the startup temperature after adding You have to mix it and you have to measure the final temperature. You can see temperature should be going down. As the temperature decreases down, what type of reaction should be? Endothermic. Why? The heat is absorbed. Heat is absorbed. So it is an endothermic reaction. Now shall we write the topic for the previous two also? This is first activity, right? Right there. Adding solid sodium hydroxide to water. First activity and exothermic. Write the topic. Adding solid sodium hydroxide. Adding solid sodium hydroxide to water. Adding solid sodium hydroxide to water. Second one. Adding a magnesium ribbon. Adding second one. Adding a magnesium ribbon to dilute HCl acid. To dilute HCl acid. Okay. Fine. Now, after the second activity of endothermic, there is an example given. Can you see? For the energy level diagram to draw. Energy level diagram to. What is the energy level diagram equation given? Can you see? Decomposition of calcium carbonate. Am I correct? Right? So, what is the decomposition of calcium carbonate? Calcium carbonate upon providing heat, supplying heat. The triangle shows the heat is supplied. So, heat is supplied means endothermic it should be, right? Will be breaking down into calcium oxide plus carbon dioxide. Okay, this is the equation. Draw the diagram. Now, as a standard, I am writing this. In any other areas, I will definitely all correct, right? How do we draw? Endothermic means who is more? Reactant or product? Products more, right? Endothermic, products more. Who is the product here? Calcium oxide plus carbon dioxide. And this is CaCO3 solid. You have to check if it is balanced. You can see one calcium, 3 oxygen, 1 plus 2, and 1 carbon, it is balanced. Now, reaction to product, the arrow will down show. Okay, you have to show the arrow head almost touching both the ends. And the heat is absorbed. Since the heat is not given, I am just writing heat is absorbed in. Okay. Fine. Look at the examples for exothermic. Go to the page 8, I guess. Take the examples. Is it 8 or 9? 6. This page. Yeah. Right. Page 5. Examples got right? Yeah, page number 5 examples. What are the examples for this exothermic reaction? Combustion of fuel. Any fuel will take kerosene oil, like all the petrol, diesel, or any sort of combusted fuel. When they are combusted, when they are being burned, they release energy. They release energy, and that is why it is getting heated surrounding the surrounding. Okay. And then neutralization reactions. Tomorrow we'll be learning about these neutralization reactions, acid-base reactions. When they neutralize, when the acid-base reactions are happening, they emit out heat. They release heat. So releasing heat, exothermic. Then it comes cellular respiration. Cellular respiration at the presence of oxygen, glucose. At the presence of oxygen, glucose. C6H12O6 at the presence of O2 breaks down into carbon dioxide, water, and energy. To balance it, we write 6. We already spoke about, okay, how it comes, right? So this is an exothermic reaction releasing energy. Okay. And production of slakline. Slakline means calcium oxide is called quicklime. What line? Quicklime. For this calcium oxide, when you add water, it becomes calcium hydroxide. Calcium hydroxide means slate lime. What line? Slate lime. Or else we term it as lime water. We don't drink lime water. Okay, we drink lime juice. We add lime juice. Drink this is not straight away. They are adding lime juice, right? They are adding for our food and all lime juice, right? So this is slake lime water, which is a base. It is a base here. Lime juice is an acid. Lime juice, acid, lime water is a base. Okay. So this reaction also emits out heat. So for quick lime, you add water, it becomes slake lime or lime water, emitting heat. So also exothermic. So can you please write this is the third point? Front of the third point, write this formula. And below this, you have a space, write this formula, write this equation. Hurry up. Page number 5. Page number 5. Page number 5. Front of the third point, you have write the similar respiration formula here. And then below, you have write the calcium carbonate law. Okay. Look at the examples for endothermic. What are the examples? Photosynthesis, opposite of respiration, right? Now you see, respiration is a breakdown. Photosynthesis is building up. And I told you, endothermic reactions are building up reactions. Carbon dioxide plus water at the presence of at the presence of sunlight. It absorbs sunlight energy, presence of chlorophyll producing glucose plus oxygen. So, absorbing energy, endothermic. And calcium carbonate, breakdown of calcium carbonate also needs energy. You have heat. Heat energy you have to provide. Absorbing energy breaks into calcium oxide, carbon dioxide. Calcium carbonate, we are giving another name. Limestone. What's stone? Limestone. Limestone, when you provide heat, will supply heat, it breaks into calcium oxide. What is the name of calcium oxide? Quicklime. I gave you the word earlier. It is quicklime. Okay, quicklime. Or else we can term it as lime also. Quicklime. Right? So for this quicklime, we merge with the previous one. For the quicklime, you add water. What happens? It gives you slake lime. So breakdown of calcium carbonate into decomposition of calcium carbonate into calcium oxide and carbon dioxide is an endothermic reaction, absorbing heat reaction. Calcium oxide you add with water becoming calcium hydroxide is an exothermic reaction. You see, two types of reaction. This is endothermic, previous one is exothermic. Write them. Hmm? Link? What? Leg. Yes. The cold pack you all keep on. Now, when you are having a fracture or something else, suddenly a cold pack you keep. Okay? Right? So, there what happens? Ice. From that, the heat will be absorbed into the body. Heat will be absorbed into the body. So to do some works within the biological functions. Okay. Absorbing heat. And photosynthesis absorb heat. When you are cooking an egg, okay, heat is, okay, what's happening? Absorbed it. Absorbing the heat only, it is changing, it's frying up, right? Because of, can you? Equation. Previous one, right? Calcium oxide plus water makes calcium hydroxide. Yeah. Right? So accordingly, what we just learned, just an example here. These are not chemical changes, it's a physical change. Ice absorb heat, ice absorbs heat and melts. Is an example for to show the endothermic reaction. But remember, this is not a reaction, okay? This is an example I have taken to observe the change, observe the difference. So ice melting is a physical change, but it shows you the absorbing of heat, endothermic. Endothermic means releasing out heat. So like burning of something, fire, so it's releasing out the heat. Okay? And finish it up. We learned about these exothermic reactions earlier, right? Was here. Exothermic we learned reactant more, products less. In this way we learned earlier, right? This can be drawn in another way also. What is the other way? Another way is there. Both the exothermic and endothermic reaction can be drawn in another way, but that is not needed for us to do. We don't want to draw, but it may come in the question. They won't ask you to draw like that, the second method that we are going to speak now, but that might be given in the question for you to give answers. So you must know both, right? That is, reactants more, look at this. Now you have to, okay? Reactants more, products less. Upward, vertically it is increasing, okay? Then you have to start from reactant the same way. Reactant should be to come down for the product, the arrow head is put down, right? Means you have to reduce down to product, right? Second method. Reducing down to product means you come down here and you mark the products. Like a staircase, you are climbing down. You are stepping down the staircase, okay, you come down from reactants to products. Because reactants more, products less. Reactants more, products less. Reactant to product, you come down. You come down. Okay? And here, who is more here? Products more, reactants less. Now, do you start from product here? No. You have to start from reactants. So, reactant is less, no? So, reactants, you are climbing up the stairs to product. You step down and you step up. So, you start from reactants and you increase up to products. So, this is for endothermic. So, exothermic can be drawn even in this way and endothermic, the second method. Clear? Okay. So, this reactant to product, you are decreasing, reactant to product, you are increasing. So, this change is the heat change. What is happening here is the heat change. That is the heat. Here it is being released, here it is being absorbed. So, we are using another word, enthalpy. What enthalpy? Enthalpy. Enthalpy we are writing, but we say it as enthalpy. Enthalpy change. Okay. Enthalpy. That is how PHY only we are writing, but we read it as enthalpy. Okay. So, enthalpy, it is the change of heat. It is a change of heat that we are using up to. Okay. But anyhow, this also is possible. So better you mark it down on your notebook where you ended up with these two. After that, we didn't write anything. Okay. After this, we wrote an example, right? Below that, draw this part, and below that example, write this. Plug it down. What next? If you know, if you have no space, put this. Same order. We have to use the first method. When we are supposed to draw, we have to use the first method only. Okay. When the questions are given, they might use either the first method or the second method. Both they might use. This one. Yeah, in MCQs they might give. Part 2 they might give. Now, in case if they are given, you should not say you don't know, right? That's what I gave. And also, if you are browsing, if you are going for the web browser, typing as exothermic and endothermic, most probably these are the diagrams comes. These are the diagrams it comes. Okay. Done? Do you want to break his teeth? Break. Are you done with this? Yes. Okay. Totally done? Fine. We take a break. You have to be here, don't be late. You have to be here. You have 10 minutes. I'll take 10 minutes and you'll have to. Okay. Because I have one more small calculation, heat chain calculation, the small part. It's up to you. 3 o'clock, sharply have to be. Yeah, after finishing up, you'll get a break. After finishing up, you'll get a break. After finishing up. Fine. Take a break. Sometimes you have to be diplomatic. So the heat change we're gonna speak about, right? You see here, a small experimental setup, but before going for the setup, let me take the containers that we are using up here. Look at this. This is a system that we are using, the apparatus that we are using. This is called polystyrene cup. What styrene cup? Polystyrene cup. Polystyrene cup. Polystyrene we are using in order to avoid the exchange of heat. The heat exchange to stop or reduce the heat exchange. Because here we are going to discuss about an experiment that speaks about the heat change. So when you are speaking about, when you are analyzing heat change, if there is heat lost out or entered in, that becomes a problem. That is an error. Because within the system, what is the heat change only you are going to speak about. So within the system, after a reaction, what is the heat change only you are going to calculate. If some others are entering or what is existing goes out, it is an error. So to avoid that exchange, you are using polystyrene top. And above that, after adding the mixtures, you are covering it up with coating. We have a thermometer and here we apply wax. So that otherwise, when you apply this hole, within the hole, also there would be small parts where the gases could be, the heat could be moving on. We have gas, and this is a stirrer, a gas rod to mix. So we have inside sodium hydroxide and hydrochloride solution. They also apply. Oh, if we shape right, then it will go. No, anyhow, okay, we're gonna keep it inside. Okay, and we are going to move it or no. So that won't be an issue there because it is adjustable in that way. And furthermore, let's say if it is connected in this way, when you rotate, it keeps moving on. Okay. Anyhow, we are using hydrochloric acid solution and sodium hydroxide solution. So I'm going to summarize this. How it happens. All game. Look here. Now you have the system. In this system, you got sodium hydroxide. Concentration is 2 moles per cubic decimeter. How do you read 2 moles per cubic decimeter. So to find out this heat change, you have a setup. In this setup, you got sodium hydroxide solution, concentration 2 moles per cubic decimeter, right? And what is the volume of that concentration? You got 50 cubic centimeters. 50 cubic centimeters. And again, you have HCl acid solution, also diluted. Both of them are diluted solutions, more water containing. So the concentration is same as the above, 2 moles per cubic decimeter. Volume is 50 cubic centimeters. Volume is 50 cubic centimeters. What are you going to do here? You are going to let the reaction happen and calculate the heat change. Okay. To find out the heat change, we need 3 factors. We need 3 factors. What are the 3 factors we need? We need MC theta. What is the formula? MC theta equals Q. Quantity of heat change, or else we can write it as capital delta H. Delta H or Q equals MC theta, or MC delta theta also we say. Mass into specific heat capacity, simple M, simple C, theta, temperature difference, or delta theta, temperature difference. Now, let me take temperature. What I do? I find out the initial temperature. What am I going to do? Measuring the initial temperature. Only one component you have, that component's temperature you can straight away take. But you got 2 components like sodium hydroxide, it's still 2 of them are there. Now, if both of them are having the same temperature, fine. But practically it won't happen. So what I do? I measure the temperature of sodium hydroxide plus temperature of HCl and I divide by 2. Both the starting temperatures, sodium hydroxide temperature, HCl temperature, I am adding and dividing by 2. Why? To get the average initial temperature. Average initial temperature. I measure. Okay. So what I measure here? Average initial temperature I measure. And then to find out the temperature difference, delta theta, what I do? Final minus initial average I do. Got it? So initial temperature, sodium hydroxide plus HCl I am dividing by 2 to get the average. That average I am reducing from the final. Final I have to record. After the reaction, maximum temperature it reaches, I have to record it from the thermometer. From that, I have to reduce this average value. So that is my delta theta. So I know the delta theta now. Okay. You understand? Delta theta I know now. Here, listen. So I know the temperature difference. Now I have 2 more parts. To measure these 2 more parts, I want to find out the mass, the total mass. You see, concentration, volume only given. Okay. Concentration, volume only given. To find out the concentration, there is to find out the mass, there is another method using concentration, but some data is reading. But using the volume, if you want to find out the mass, there is a formula. What is the formula? Mass volume is connected with the formula. Density formula. What is the density formula? Density equals mass over volume. Density equals mass over volume. So if you know the density and volume, you can find out the mass. You can find out the mass. If you know the density and volume, you can find out the mass. But the thing is, 2 components, right? Both of them are different in densities. And if I'm going to drag both the densities, my the calculation becomes complicated. So what I do, I'm making 3 assumptions. What I do? I make 3 assumptions. Number 1, I'm going to take the density of the mixture is equal to density of water. Since I told you already earlier, both of them are diluted, right? More water added, right? Since more water added, more water it contains. So water's density, I'm making equal to the density of the entire mixture. The total mixture's density, I'm going to assume to be equal to water's density. Water's density is equal to 1000 kilograms per cubic meter. Or else for smaller values, 1 gram per cubic centimeter. 1 gram per cubic centimeter. And I want to use this. Why? It is given in cubic centimeters. Okay, cubic centimeters. This is the first assumption. Here's the first assumption. Alright. So, second assumption is, now using this, I can find out the mass. Theta I. Okay, theta already found. Mass we can find using this. and C. Second assumption I made, specific heat capacity of the mixture. 1 kilogram of water to increase the temperature by 1 degree Celsius. Specific heat capacity means 1 kilogram of water you have, 30 to 31, 1 unit of temperature to increase how much heat you have to provide. That is specific heat capacity. So this is equal to 4,200 joules per kilogram per degree Celsius. So we make another assumption, mixtures specific heat capacity is equal to water specific heat capacity. Why? Otherwise you have to make them both separately. That's complicated. So using that, you know the MC. So MC theta you can apply to find out Q. What is the third assumption? There is no heat loss. There is no heat loss. So we say total heat change is used to increase the temperature or else decrease the temperature. Any of them could be happening. If it is an exothermic reaction, to increase the temperature. Why in exothermic reaction only the temperature will be increasing? That means what is the heat change happen? That entire heat change, let's say 100 units of heat change is happen. That entire 100 units of heat change is used only to increase the temperature. In exothermic. Or in endothermic, that entire 100 units of heat is used to decrease the temperature. No any other works. And no heat loss. You understand my point? So, what is the work done? It is totally used to increase the temperature. Okay? Totally used to increase the temperature in exothermic. And totally used to decrease the temperature in endothermic. Got the point? Okay, so accordingly, there is no heat loss. No heat loss. Total heat is used to increase the temperature in exothermic, decrease the temperature in endothermic, no heat loss. This is the third assumption. And how do we make it a fair test? Using polystyrene cup. Can you remember earlier I told you polystyrene cup we are using? Why? No heat exchange. Reducing or stopping the heat loss. So we make it a fair test. Okay. So these are the three assumptions we make. Using the three assumptions, we are going to calculate this. We are going to calculate this. Okay. So before we go for the calculations, look at your tube. Look at your tube. Go to the page number 4. Page number 4. Go to page number 4. Can you say there's a text box given? Above the text box, there's a space, right? Above the text box, there's a blank space, right? About 2 to 3 line space is there, right? Okay. Can you see that? After the first passage? Right. There we write this part. Only this area, okay? You can write this. About the average temperature. This area, only this area, okay? This part completely. Don't take the upper and the lower ones. Yes, above the text box. Sorry? Yes. That is standard way. The specific heat capacity of body is 4,000 points. That's the table. Okay. So the specific heat capacity of body is already known. Something like after one this value. This is an already known standard value, right? Like that, this is a standard value for what? This is what we are using. Okay. And that is why it becomes easy for us to calculate. Otherwise, we have to take both of them separately and get the average. It is complicated. We can't get the average also there. Only. right? Right. Now, there's a text box then. There's a text box, right? There you write this Q equals MC theta, make it big fonts. Okay, the font size you increase, the letter size increase. Q equals MC theta. That is the only thing. And next to that, what is MC theta is given in words. Okay, now you know M is the mass, C is the specific heat capacity, theta, it is the temperature difference. Or delta theta also you can find. Okay. Fine. Right. Now read what is given there down. Read what is given there down. What is given there? Assume that temperature difference is 10 degrees Celsius. Highlight it. Otherwise, you don't know what the question is. Assume that 10 degrees Celsius is the temperature difference. Now we are going to find out the quantity of heat change. Okay. Look at this. I want to find out Q equals MC theta. But look here. Look here. Now theta, you know, right? Temperature difference is 10. Who is C? Specific heat capacity. I can apply this 4,200 straight away, right? Why? That is the assumption. But the mass, do we know? No, we know the density. What I do? First, I find out the mass. So I'm going to write total volume of mixture. What is the total volume of mixture? You have 50 cubic centimeter plus 50 cubic centimeter. Means 100 cubic centimeters, correct? 50 plus 50, volume 50, 100 is the total. Okay. Within the container, you got 100 cubic centimeters. What is the first assumption? The density of the mixture is equal to density of water. So, I'm going to take the density of mixture 1 gram per cubic centimeter. 1 gram per cubic centimeter. Hence, total mass is equal to D equals M over V. So, M is equal to D into V. Correct? Density is 1 gram per cubic centimeter. Volume how much? 100. 1 into 100? 100 grams. So what is the total mass? 100. Is it hard? What did we do? We found the total volume. You know, this question, this heat change question comes the same. Values may be different. Okay. Comes the same way. Probably sodium hydroxide, HCl, or any other acids and bases they come. Right? Both you have to get first. Very simple. Both the volume. Sometimes 40, 60 given. Or 80, 120 given. So anything, for example, get the total. Total multiplied by the density of water. Why? Density of water is the density of mixture. We assume that, right? So 1 into 100, 100 grams. Now I apply Q equals MC theta to find out the quantity of heat. Mass is 100, but I can't apply 100. Why? It's in grams. I have to take it in kilograms. What I do? Divide by 1000. Specific heat capacity 4,200 joules per kilogram per degree Celsius. What is the temperature difference? 10 degrees Celsius given, right? 10 degrees given. We highlighted that. Now you simplify 1, 2, 3, 1, 2, 3. 420 into 10, 4,200 joules of energy heat is a heat change. So what is the heat change during this reaction? When you use 50 cubic centimeter each, when you mix them, what is the heat change happening? 4,200. 4,200 joules. Did you understand that? Is that clear? Please write this down. The space is given there after what we have highlighted, right? Okay. Left side, right side. Now you know. Now try to recall and write it alone. Right. Now again, next one, the last one. This part is given. Okay. It gives you long statements, right? Go to the next page. And I have divided by a straight line, right? Left side we write. Sorry, right side we are right. What are we going to write? I'm going to take this off. Can you read the first line? What the first line says? Log statements given, right? Log statements. We are going to write it using equations. Okay. First calculation is given then. What is the first calculation? Can I see the same? After the first two lines, amount of moles of sodium hydroxide in 50 cubic centimeters up to moles per cubic decimeter sodium hydroxide solution. Very short line, no? Right. So, if you are okay to write such statements, you are fine in that method. Otherwise, okay, in front of that you have to write. What I do for sodium hydroxide, and applying C equals N over V. What is the formula? C equals N over V. Concentration equal moles over volume. I know the volume, I know the concentration. So can't we find out the moles? Can. So N equals C into V. Concentration is given 2 moles per cubic decimeter into volume is given 50 cubic centimeter. So I have to divide by 1000 to make it cubic decimeter. 2 into 50, 100 over 1000, 0.1 mole. So in this, how much moles of sodium hydroxide you have? 0.1 moles. 0.1 moles. Got it? Same way the second line. For HCl also applying, moles equal concentration into volume. How much is the concentration? Same, 2 moles per cubic decimeter. Volume 50 divided by 1000 cubic decimeter. 0.1. So how much moles of HCl you have? Same, 0.1. 0.1 moles of HCl you have. Okay. Now, what's the next? Next one I have write a small statement. That is, you have 0.1 mole of blue. Okay, each 0.1. Now you see 0.1 mole of sodium hydroxide reacts with 0.1 mole of HCl. Gives you 4200 joules of heat. Correct? Earlier it was giving me 4200, right? Earlier, previous calculation gave you 4200, right? Right. Now, 0.1 to 0.1 when they are reacting, what is the heat change? 4400. How did we find? Using the Q equals MC theta earlier, we found for this particular experiment, right? It was 4200. Now our point is, what if it is 1 mole of sodium hydroxide reacting with 1 mole of HCl? How much do you think? Let's check with your maths knowledge. Give me the answer. 0.1 to 0.1 reaction is 4200. What if it is 1 mole to 1 mole? 42,000. Right? 5 pens equal 100 for an example. It won't be. Imagine. Then 1 is equal to 100 over 5. Correct? So, point 1 to point 1 is 4200 means 1 to 1 how much? 4200 divided by 11. Yes. Right? 42,000 joules. 42,000 joules means 42 kilojoules. 42 kilojoules. Is that clear now? This is how the questions come. Okay. Moles we want to find out concentration into volume. Okay, concentration into volume. Find out the moles. That mole, how much heat given. If they ask you for 5 moles, then you have to multiply this by 5. You want to divide by 0.1 and multiply by 5. If it is for 10 moles, you have to multiply by plus. Is that clear? Clear the point? Very simple when you are using the equations. Otherwise, long statements you have to write. But you can't just write. You have to mark force what you write also. Yes. 4,200 divided by 40,000. Is that clear now? Shall I write it down? Write opposite of the statements. Please write it down. Hurry. This fellow couldn't escape today. I noticed for 2 weeks. Done? So this Q equals MC theta once again will be taken the next lesson also, next chapter also. There only we are going to do some general calculations using Q equals MC theta. This is related to the experiment. This comes in structure essay question, essay type question both. Okay. You have to practice it. Going home, you have to practice this. Every day we say go home, revise, do practice. If you are not, okay, your fault. Okay, your fault. Remember that.